Hello students, myself S. Jyoti Kiran, Assistant Professor, Government First Grade College, Tiptur. Today I am going to explain Cayley-Hamilton Theorem, one of the important theorem. The statement of the theorem is, every square matrix satisfies its own characteristics equation. Let us see the proof of the theorem. Here, let A be a square matrix of order n and let us take the polynomial equation a minus lambda I is equal to minus 1 to the power of n. The characteristic equation is minus 1 to the power of n c naught lambda to the power of n plus c1 lambda to the power of n minus 1 plus cn. The expansion of this equation, characteristic polynomial equation. In this equation 1, where here the constant c naught, c1, cn are the scalars. Hence, the characteristic equation of A is given by determinant of A minus lambda I, which is equal to 0. For that, the above equation 1 becomes C naught lambda to the power of n minus 1 to the power of n becomes 0. Here this equation 1 becomes C naught lambda to the power of n plus C1 lambda to the power of n minus 1 plus etc. Cn is equal to 0 and is satisfies by lambda is equal to A. Therefore, we have to prove that C naught A lambda to the power of n plus C1 A power of n minus 1 lambda to the power of n minus 1 plus etc. The last term is Cn into I, where I and 0 are respectively called as a unit matrix and null matrix of order n. Since the elements of A minus lambda I are at most of the first degree in lambda, the elements of adjoint of A minus lambda I are polynomial in lambda of degree at most n minus 1. Therefore, adjoint of A minus lambda I can be expressed as a matrix polynomial of degree n minus 1 in lambda. Let us take adjoint of A minus lambda I. Expansion is b n minus 1 lambda to the power of n minus 1 plus b n minus 2 lambda to the power of n minus 2 plus etc. The last term plus b1 lambda plus after b1 b naught is there. So in this equation b naught, b1, bn minus 1 are the matrices of order n cross n and their elements being polynomial in aij. So we know that A into adjoint of A is nothing but determinant of A into I. So A into adjoint of A is replace A by A minus lambda I, adjoint of A minus lambda I, which is equal to determinant of A minus lambda I into I. Then A minus lambda I, then adjoint of A minus lambda I, already we write the equation. This is nothing but Bn minus 1 lambda to the power of n minus 1 plus Bn minus 2 lambda to the power of n minus 2 plus etc. Bn lambda plus B naught, which is equal to then minus 1 to all in equation 1 A determinant of A minus lambda I in equation 1 is there. Here minus 1 to the power of n C naught lambda n plus C1 lambda to the power of n minus 1 plus Cn into I. So equating the coefficients of like power of lambda on both the sides we get. So here coefficients of like power of lambda we have to equate in the above equation. So first we get the term minus bn minus 1 is equal to minus 1 to the power of n c naught I. Next coefficient is ab n minus 1 minus bn minus 2 is equal to minus 1 to the power of n c1 I. Again ab n minus 2 is minus bn minus 2 is equal to minus 1 to the power of n c2 I, etc. Finally we get the last term, that is a b naught is equal to minus 1 to the power of n Cn I. Then pre-multiplying the above equations respectively by an, then it will become an minus 1, an minus 2. Finally, the last term becomes ai, and adding we get a power of n. On LHS, it is multiplied by a power of n minus bn minus 1 plus a power of n minus 1 ab n minus 1 minus bn minus 2 etc. which is equal to RHS becomes minus 1 to the power of n C naught a power of n plus C1 a power of n minus 1 plus C2 a power of n minus 2 etc. plus Cn into I. So this is minus 1 to the power of n Cn into I. So again this will becomes LHS becomes 0, then which is equal to minus 1 to the power of n C naught a power of n plus C1 a power of n minus 1 plus C2 a power of n minus 2 plus Cn I. Then this will becomes 0, minus 1 to the power of n becomes 0. This equation will remains C naught a power of n plus C1 a power of n minus 1 plus C2 a power of n minus 2 plus Cn I is equal to 0. That is, A satisfies the characteristic equation determinant of A minus lambda I is equal to 0. Hence the Cayley-Hamilton theorem is proved. Hence the Cayley-Hamilton theorem is proved. Thank you.